To better understand Young's double slit experiment, I suggest you to view the interference video before this. In 1800s, English scientist Thomas Young obtained convincing evidence for the wave nature of light and was even able to measure wavelengths of visible light. In his historic experiment, monochromatic light passes through a single narrow slit and falls on two closely spaced narrow slits S1 and S2. These two slits act as coherent sources of light waves that interfere constructively and destructively at different points on a screen, and they produce a pattern of alternating dark and bright fringes. The purpose of single slit is to ensure that only light from one direction falls on the double slit. Without it, light coming from different directions will cause the pattern on the screen to be washed out. Now, to help explain the origin of the bright and dark fringes, let's take a look at the top view of the double slit and the screen. First, suppose waves from each slit travel to directly opposite the midpoints between two slits. At this location, the path these two wave paths, R1 and R2, are equal to each other. R1 equals R2, which means they both meet at that point in phase, and so they will interfere constructively, which will cause a bright fringe right here. Let's quickly recall the conditions for constructive interference and destructive interference. For constructive interference, the condition is when R2 minus R1 equals an integer number of wavelengths, and a destructive interference condition is when the path length difference is m plus 1/2 lambda, where in both cases m equals 0, positive, negative 1, plus, minus 2, and so on. So for just to make sure that what I just said, the constructive interference happens in our case, so R2 minus R1 equals 0, which is a constructive interference when m equals 0. Now, another place where constructive interference will happen is when the wave from the source 2 travels one full lambda extra path length. If we consider the length of a wave of the path that comes from the source slit 1 as an R1, then the path length of the second wave from the slit 2 should be R1 plus lambda. So in reality, I could put a line in here, and this much should be a lambda. So in this case, we have R2 minus R1 equals 1 lambda, which is also constructive interference. Well, obviously, a destructive interference will cause dark fringes. And a point where destructive interference will happen is when the wave from slit 2 travels half a wavelength extra. Destructive interference creates other dark fringes on both sides of the center wherever the difference between R1 and R2 equals an odd integer number of half wavelengths, like 1/2 lambda, 3/2 lambda, 5/2 lambda, and so on. And obviously the bright fringes will happen on the both sides of the center as well. The position of the fringes observed on the screen can be actually calculated. For that, let's take a closer look on this. If the screen is located far away compared with the distance between two slits, let's call it D, then the lines L1 and L2 are nearly parallel. Being nearly parallel, these lines make approximately equal angles with the horizontal. Let's call these angles theta. To better picture the situation, I drew a little bit more magnified picture here. So we have our path lengths R1 and R2, and the difference between these two path lengths, so let's call it delta R, would be this distance from each other. Now, according to geometry, we can say that the angle right here is also a theta. Then from here, I can find that delta R equals D times sine theta, since we have a right triangle here. So if we recall conditions for the interference, here we have delta R equals m lambda for constructive interference, and delta R equals m plus 1/2 lambda for destructive interference. So I can write here delta R equals d sine theta. And from here, I can say if d sine theta equals m lambda, then we have a constructive interference, which means it's a bright fringe. And d sine theta equals m plus 1/2 lambda for destructive, which means a dark fringe. So here we can actually find out by theta where the bright and dark fringes are. For example, let's do a little bit analysis here. When theta equals 0, we have a bright fringe. That's a bright fringe, and it's known as a 0-order maxima. When we use m equals plus minus 1, then we say this is a 1st-order maxima. So on the screen, we will see, let's say, if the m on the left side and m plus 1/2 we put on the second, on the right side, which is destructive here, and constructive on the left. Then let's say this is m equals 0. This would be positive 1 plus 2 plus 3. M equals minus 1 minus 2 minus 3. For the dark fringes, we would have positive 1/2, positive 3/2, 5/2, and then going down, this one would be negative 1/2, negative 3/2, negative 5/2. Now we can also find the positions of bright fringes on the screen. So if we want to find that, let's redraw our slits in the screen. Let's suppose that the screen is on vertical on the y-axis, and it has a r distance from the slits. And we know that the central bright fringe is right here, right in front of the midpoint from between the two slits, the distance between two slits. And then if we want to, this is corresponding to theta equals 0, central bright fringe. And then let's suppose that we want to find out the bright fringe, the position of the bright fringe, mth order bright fringe. So I would probably have a negative m on this other side. And let's suppose that the distance from the bright fringe to the mth bright fringe is, let's call it ym. And the corresponding angle, let's call it theta m. So this one should be also theta m. Now, if we focus on the top right triangle, we should be able. The top triangle looks like this, where here we have a theta m. Here we have on this side r, on the opposite to the theta we have a ym. I should be able to write that ym, which is the position of the mth order bright fringe on the screen, should equal r times tangent theta m. So if we consider that ym is way smaller than the distance between the screen and the slits, then we can say approximate the tangent theta as sine theta. Obviously, when we say ym is way smaller than r, we are thinking of theta m to be very small angle. Then I can rewrite my equation for ym equals r times sine theta. But now let's recall, for constructive interference, or for a bright fringe to happen, we need to have d sine theta, where the d is little distance between two slits right here, should equal m times lambda. So from here I can find sine theta. I'm gonna equals m lambda over d. So if I plug this one into my equation, I will get ym for bright fringe equals r m lambda over d, and this is for a bright fringe. Similarly, I can find YM for the dark fringe. Allow me to write here dark and add bright in here. Did I write right? It's supposed to be bright, not rewrite. That's funny. So bright. So let me just write it in here as well, bright. Okay, so going back to our position of our dark fringes, that would be R M plus 1/2 lambda over D. So this is how you find the positions for the bright fringe and position for the dark fringe on the screen. I would like to emphasize again, historically, Young's experiment provided very, very strong evidence that light has a wave-like character. If light behaved only as a stream of tiny particles, as others believed at that time, then the two slits would deliver the light energy into only two bright fringes located directly opposite the slits on the screen. Instead, Young's experiment shows that wave interference redistributes the energy from the two slits into many bright fringes. Thanks for watching. Stay tuned for more to come. So my next video will be on intensity in the interference pattern.